Well, good morning, good afternoon, or good evening, depending upon where you are in this world, and welcome to today's webinar. I'm Charlene O'Hanlon, moderator for the event, and I welcome you. We have a great webinar today. I'm really excited about this one, but before we get started, do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you missed any or all of the event, you'll be able to access it afterwards on demand. We're going to be sending out an email that includes a link to access the webinar on demand, as well as the slides. And we are taking questions from the audience. So if you have a question for our panelists today, please don't hesitate. Just use your GoToWebinar control panel, submit your questions, and we'll take probably about 15 minutes or so near the end of the presentation and go through the audience questions. Okay, with that, let's go ahead and kick off today's webinar. What we got wrong? Lessons from the birth of microservices at Google. Our speaker today is Ben Siegelman, who is CEO and co-founder of Lightstep. Hi, Ben, how are you? Thanks for joining me.
I'm great. Thanks for having me. I'm excited about this talk. It's probably helpful if I give a little tiny bit of background about myself beyond my title right now. I started at Google in 2003 as a fresh out of college new grad. My previous full-time employment had been literally at an ice cream shop, so I had no idea what I was getting myself into. But I
Yeah,
had
a little different.
yeah, it was a lot different, but I really enjoyed my time there. And in the experience of working at Google in that era was something that certainly formed my own opinions about how systems should be built and also how they shouldn't be built. And there's a lot of things that we're seeing in the larger market right now that resemble what we were doing at Google, but as I'll talk about in this presentation, I think for different reasons than why we did things at Google. So anyway, I thought it would be helpful to talk a little bit about what we did and what we didn't do and how things that we experienced at Google could be applied to the rest of the world. So that's what this talk is all about, and I hope that it's interesting to people. And I'd really encourage folks to ask questions. I've intentionally left some space at the end, and I love getting direct questions about things and challenge me on things or whatever it is that you'd like to do. So without further ado, what we got wrong. So let's just talk about the setting at the time, because I think it's a little bit difficult to remember. And we have employees at Lightstep who were born after Java was invented and just a few years before this. So who knows? Some of you may not even remember it. But this is what Larry and Sergey look like. The company when I joined was still, well, it's not entirely fair to say when I joined, but a year or two before I joined, the company was still betting on the Google Search appliance as their big business. Things were very early. They had developed some incredible technology and had a clear market leadership in web search, but that was kind of where things were. By and large, from an engineering standpoint, a lot of the decisions that were being made came down to this issue, which is that at the time, if you wanted to build internet software, you had to build your own data centers, and you had to assemble those data centers out of racks of computers. And the ones that most people were buying were made by Sun Microsystems and were actually really marvelous to develop on, but just ungodly expensive. And so the folks at Google felt that maybe they could do better from a ROI standpoint and build on commodity hardware with Linux. And they weren't the only people trying to do this, but it does present a problem. So the Sun boxes are so expensive was what they were running away from. What they ended up with instead was a bunch of Linux boxes, which were incredibly unreliable. And that inspired a style of software development that was designed to be resilient to failure at the hardware level, and where previously people had used things like Solaris and expensive big metal hardware to have built-in resiliency at the kernel layer using multiplex hardware. The idea here was that they would write software in userland that would be able to accommodate frequent failures of entire swaths of machines. And that was a real innovation in terms of their thinking and led to some of the most impressive technology I think Google developed in its entire lifetime was in that first 5 years or so when they were developing a new type of software that was built to run at scale on low-cost commodity hardware with low-cost open source operating systems. So this is something that we didn't hear in 2001. Absolutely nobody said, let's do what's on GitHub, because it didn't exist. And in fact, there was open source software, of course, but this is kind of what open source software looked like in 2001. This is, I went to the Wayback Machine and took a screenshot of the GNU and Apache web pages from that era. And there was some stuff. It wasn't like there was nothing, but it certainly wasn't the sort of building blocks that you would use to build a distributed system. That you could use fragments of operating systems and so forth, but that was about it. So people really had no choice but to build things from scratch, and that's an important thing to understand, because I think if Google had been founded today, you know, controlling for markets and stuff like that, it wouldn't have made any sense to do what they did. They built a lot of things in-house and developed a culture that was not invented here, in the sense that there's a distrust of using things that weren't invented completely from the bottom up at Google. But that was a decision that really only made sense in that time and place. And the world that we're living in now is quite different. And in a moment, I'll talk about why this decision to build almost everything up from scratch had some benefits, but also created an ecosystem at Google that I think ultimately led to some questionable design decisions down the road. So let's think about the engineering constraints that they had at the time. They had to DIY, they had to do it yourself because of some wacky requirements and a lack of alternatives. So by wacky requirements, I mean that they had to build something that could index the entire internet, and no one had done that before. So they couldn't find some kind of off-the-shelf database that was capable of ingesting that much information. They had to scale horizontally because they're using low-cost commodity hardware that was going to fail all the time. And that led to an environment, along with the fact they had to build everything in-house, that in conjunction with these cultural hallmarks, which were that they're intellectually really rigorous. They had a lot of people who had, many PhDs and were really aspirational about the kind of systems they wanted to build, and had a background in systems research, and frankly were maybe a little bit overconfident or even vain about how well they were going to do things, that they went and invented crazy new stuff from scratch. And so what happened? This is part two. We ended up with this explosion of infrastructure projects at Google. The culture there really idolized things that were being created by the big brains at Google. Like there, at this point, I think even outside of Google are somewhat well-known folks like Jeff Dean and Sanjay Gamawat, Luis Barossa, Mike Burrows, Sharon Pearl. These people did some incredible work creating systems like GFS, which was Google's distributed file system, Bigtable, which is kind of like Google's version of Cassandra, MapReduce, which I think everyone knows. Borg was their giant cluster level scheduler. Mustang was the thing that actually serves up does the brunt of the work for web search queries. Smartass isn't as well known, but I think has as much to do with Google's profit margin as anything on the ad side. It's an incredibly sophisticated pipeline for machine learning based ads ranking. These projects are just six of probably a dozen or so things that were really kind of monumental achievements, and the ones that they wrote papers about all became instant classics in terms of systems research. And what I'd emphasize is that the staffing for these projects was actually pretty small compared to the headcount for the company. These infrastructure projects were what the rest of us kind of looked to and idolized in the way that we were building our own software, which didn't have necessarily the same kinds of requirements that these projects had in terms of scale and reliability. And that ended up, I think, leading Google in the direction of something that looks a lot like microservices. So these are the common characteristics of these most admired projects. They had to scale horizontally. So there was an intense desire from a design standpoint to figure out where those horizontal scale points were and make sure that they could scale across machines, so you wouldn't have to buy a giant machine to house all of the data in any one part of it. There was also a desire as software engineers to factor things out really beautifully and elegantly, and to optimize for both latency and for throughput. And this led to a completely separate layer for RPC, some remote procedure calls, service discovery, load balancing. Over time, we added things like distributed tracing, authentication. All that stuff was really beautifully factored so that essentially every single service at Google was using the same piece of software to do each one of these separate concerns. And then there was a desire to do something similar to what we now call CI/CD. It wasn't quite to the point of every commit, but healthy projects that Google were releasing once a week, and maybe once every 2 weeks. And that doesn't sound controversial now, but at the time was actually way ahead of the curve, I think. So this really sounds a lot like what we talk about now. If you go to KubeCon and hear the sorts of things people are talking about with microservices and Kubernetes and service mesh and things like that, this is very familiar territory. And this is what we were all emulating when we were building out whatever it was we were working on. I went on at Google, I did end up working on building out the Dapper project and the Monarch project, which are large distributed monitoring systems. When I started there, I was just working on some total backwater thing in the ads world that nobody's heard of, and I was trying to do these exact things for that backwater project that actually had very little traffic as well. So now we're getting into what the lessons are from this experience. And the first one in my mind, and I've hinted at this already, is that you should always know why you're doing what you're doing, but especially if you're adopting microservices, you should know why you're adopting microservices, because there are different reasons to do it, and they're valid, but you should know which one you're choosing, and you should understand why it's actually applicable in your situation. So we hosted a talk a few months ago from Vijay Gill, who's the SVP of engineering at Databricks and was formerly an SVP at Salesforce and Microsoft and Google, a real, a true seasoned engineering leader. And he gave this great talk that was, I think, I don't remember the exact title, but it was essentially the only good reason to adopt microservices. And his argument, which I generally agree with, is that microservices are useful because of engineering management and because of communication. And the observation is that you will ship your org chart. It's very difficult not to end up doing that. If you're building a functional engineering organization with hundreds of employees, you want to have the teams operate independently, and you want to minimize the amount of human communication that's involved with software development and release and operation. And so this leads to this model where you have a service team that maintains their component and releases it separate from the others. This is essentially a management issue. I'm not saying it's not important. Management's super important, but it's completely different than the reason that microservices or something like them were developed at Google. And I often hear people talking about microservices in terms of computer science, which is a really different reason to adopt microservices, and is in fact what Google is initially motivated by. So at Google, I think we had what I would refer to as accidental microservices. I maintain that microservices are absolutely the right way to solve the engineering management problem for applications that involve hundreds of engineers. I would also maintain that a lot of the motivation that I hear from engineers working on them has to do with computer science, and it worries me a little bit in that if you pursue the computer science angle, you can end up barking up the wrong tree, and I think we definitely saw that at Google. So the basic mantra at Google, and I experienced this pain firsthand when I was working on infrastructure that was meant to be used by the entire company, was that we should build what's best for search and ads because they were the biggest, and so their requirements would lead us to the best solution. And so there's this idea that the biggest thing is the best thing. That is totally false in my mind. Actually, ironically, it was a lesson I learned from Jeff Dean at Google, was that you can't really design a system for more than 3 orders of magnitude of scale and expect it to be appropriate. And So if you have something like web search, which I actually don't even want to try to quote the correct number, but let's say it's order of hundreds of millions of queries per second in terms of the system. It's really an overwhelming workload. You compare that order of magnitude to something like, let's say, Google Checkout, for instance, which certainly processes many transactions, but because they're purchases, there aren't going to be as many as web searches. Those are very different systems. And it's not realistic to expect the bigger thing to necessarily be better. It's going to have fewer features because it has to scale. And this is something that causes a lot of problems. The reality is that what's best for search and ads is best for just the massive planet scale services. So it is true the search and ad solutions were good for Gmail, good for, I don't know, take your pick of brand name Google services that operate with a lot of read traffic. It was great for those things, but it wasn't good for the other things, in that the design decisions that we were making for the large systems and the large products at Google were actually very constraining and resulted in this. There's this incredible video inside Google, which unfortunately I ironically Googled it and couldn't find a copy of it outside of the company, but someone made this video internally that was kind of like a platonic dialogue between these two cartoon characters talking about how one of them just wanted to serve 5 terabytes of data, which is a little more than you can fit in memory on a single machine, but it shouldn't be a big deal. And the reality is that if you wanted to build a system that did this at Google, even with low traffic, the number of hurdles you had to jump through would take a competent engineering team 3 to 6 months just to check all the boxes to launch this thing, even though from first principles, it's actually not that difficult to do this using off-the-shelf software that now is available on GitHub. And this is a real problem. So you have this issue where people build microservices with a desire to scale with the best of them. I think you should always know how much you need to scale to, and you shouldn't design past that. Or at least you shouldn't design more than 10x past that, or whatever it is that your business requirements are. And I think that there's often a desire to emulate what really large companies are doing with an assumption that that's better. I do not think that's the case. I think what they're doing is good if you need to operate at that scale, and if you don't, you should be very cautious about that. And so when microservices are adopted for their scaling properties, you often end up following design decisions that weren't necessarily meant for lower scale microservice development, which again is more about the velocity of your engineering team and the frequency of releases. And frequency of releases in horizontal scaling are very different requirements, and they'll lead you in different directions, even though from a block diagram standpoint, you'll end up with similar architectures. So lesson 2, serverless is my absolute, by far least favorite buzzword in our industry right now. I don't have an issue with the technology, but the buzzword drives me crazy because it doesn't mean anything. I mean, examples of serverless things would be like a fish is serverless, a taxi cab is serverless. There are many things that aren't a server, and yet, they're not what we think of as serverless. But when we're talking about serverless, we're usually talking about functions as a service, something like Amazon Lambda or Google Cloud Functions. They still run on servers. And there's this desire that I see in the industry right now that repeats some things I saw at Google 10, 15 years ago, to get things to be smaller and smaller and smaller and smaller. This idea that microservices are good, well, let's go smaller and get something that's as small as a single function. There definitely are times when that's appropriate, and I'm not arguing by any means that they shouldn't be used, but that should be done knowingly. This is another tidbit that I think I've used this name 3 times already, but it's another Jeff Dean nugget. It's numbers every engineer should know. I'm not expecting anyone to read this slide right now, but the idea is that it's difficult as an engineer to remember with all these incredibly small and incredibly large numbers, whichever, if you're talking about latency, or if you're talking about how many bytes you can fit in RAM right now, it's hard to remember the orders of magnitude of the various things that we have to use as we're making estimates. And I'm going to pull out, this is another version of this, which is visual. It's great, and everyone should look at this. It's actually really interesting, and every time I read it, I remember something that I had previously forgotten. But I want to pull out 2 things specifically. Accessing main memory for a cache miss takes about 100 nanoseconds. So that's 1/10 of a microsecond. And doing a round trip from one VM to another within the same data center, so you're not hopping over the wide area network, that takes 500,000 nanoseconds. So this is basically the difference between accessing main memory and having two serverless functions talk to each other. And it's totally fine if, if it's fine, but a lot of times I see people splitting things up where they essentially take something that should be a local cache and they put it into its own serverless function. And then they're surprised when things either become very slow or very expensive in that you need to scale out throughput, and you've just basically, added 4 orders of magnitude of cost to your cache access. So I think that we should be careful about this direction towards getting smaller and smaller and smaller. At some point, things get small enough that you start, uh, you know, breaking down some very useful abstractions like caches. So I do think that there are times when you can get away with things that are embarrassingly parallel and have a single function that's operating in a latency sensitive service. And fast is perfect for those. By fast, I mean functions as a service. But when you're using fast for things like caching, be careful. Make sure you know what you're doing and make sure you understand what you're getting yourself into, because accessing one function from another in a local machine is no big deal. Accessing one function from another in a cloud infrastructure is a really different story. And that's something I think I'm seeing that trend happening in the outside world right now, and I think we should be really careful about it. Okay, lesson 3. So there's this idea of independence, and I was talking about it earlier, that the reason why most organizations should adopt microservices is for their teams to be independent. And I think that's totally valid, and I'm fully supportive of it. But what kind of independence are we talking about? And there's this analogy I'd like to draw between hippies and ants. So here's a picture of hippies. I want it for the record. I love hippies. My parents were hippies. They're great. Like, no issue about hippies. But this was the epitome of independence. Everyone gets to be who they are and make their own decisions, and we have free will. And it can be really lovely culturally, at least when it's going well. I don't think that's the way we should be developing microservices. We shouldn't let every team make completely independent decisions. They should certainly make independent decisions about their business logic and within certain constraints how they design their systems. But I think it's better to think about something like an ant colony, where you have indeed these individual workers can go out and forage, and if they find something, they can eat it, and then after they do so, they have all sorts of built-in security functions to warn each other of danger and to alert each other when they've just discovered something with their pheromone trails. And there's a bunch of code that's built into ants at the genetic level to allow them to operate communally in a way that's actually quite multiplicative. And you see similar things with microservices in that you want to be able to have a single layer to do monitoring, a single layer to do security, service discovery, load balancing, those sorts of things. What you don't want to have is a situation where each team gets to make separate decisions about those cross-cutting concerns. So things that you need to understand at the platform layer should be, I actually don't have a strong opinion about which ones you choose, but your organization should or almost must choose a short list, hopefully one, but certainly not more than 3 options for your organization to use when you're talking about standards and APIs to bind to for these cross-cutting concerns like security and monitoring and deployment. And one thing I've seen in the very early adopters for microservices is a tendency to allow engineering teams to choose those separately, which then creates massive organizational problems when it comes time to actually operate these systems, because you have to do everything bespoke for every team, and the tax of figuring that out on a team-by-team basis undoes most of the benefits of microservices in the first place. I think to Google's credit, they got this part right in spades. I mean, there's really just one way to do things in each of the major languages, and there are only really 2.5 languages you could choose from. So they did this brilliantly, and I think it was a large part of Google's success at getting new services written had to do with this decision of theirs. So in terms of observability and monitoring, which is something that I'm biased towards, I have 2 final lessons, and then I'll open this up for questions, and hopefully we'll have plenty of time for those. So the first one is to beware of what I'd call giant dashboards. probably it's best if I show what I mean by this. So here's actually a picture of a dashboard that we've seen in production at Lightstep. Names have been removed to protect the innocent, but here you see a picture of 8 different statistical time series charts. This is what dashboards look like. There was a regression. I would ask people, take a moment, look at these graphs, and decide like when did the regression happen. And I think that's pretty easy. It was, around 12 or so. In some places it shows up a little before 12. Some places it shows up a little after 12 in terms of where the spike is. But you can see it in all of these charts. And I can attest that there were another dozen of these, if not more, that showed the same issue. So that's great. So I think time series data is effective at capturing regressions. And in fact, you can usually see them in many places. The challenge is that I don't know which one is the culprit. And the truth is, I don't mean just that it's beyond me asking you as an audience to look at this and figure out which one is the culprit. I actually have no idea either, because I don't know how you could possibly know that. I don't know how you could possibly know that. And that's something that's really, really important to understand, that if you move in the direction of building systems like the ones we built at Google, we saw this ourselves. Our dashboards got bigger and bigger and bigger and bigger because we had more and more time series data that might be relevant in some way. And it got to a point where first of all, signal to noise was incredibly low because you had literally pages of these charts. And then moreover, if there was an incident, it wasn't that it didn't show up. You definitely found the incident in terms of what time it happened at, but you had no idea where it came from. And you had so many different hypotheses to test with these different charts, all of which are just statistics. So they're not even really describing what happened. They're just giving you some kind of indication of a side effect. That it was often extremely difficult to understand what had actually gone wrong. And so you ended up calling up, the expert for a given team who hopefully still worked at the company and still worked on a project to explain, if this chart is spiking, what does that actually mean? And maybe they'll know. And that's not a very sustainable way to manage a large system, especially when failures in component X can have side effects in component Z that's very far from X in the system. So I actually would contend that observability boils down to 2 activities, and I think we need to be a lot more rigorous about the way that we describe these 2 activities. The first one is the detection of critical signals. That's kind of what I was getting at with the time series data. Sometimes I think we forget whether we're trying to detect a signal that matters to us, or if we're trying to use time series data to prepare for a root cause analysis that's going to take place later. But I think it's probably best to restrict time series data to the detection of critical signals. So these are things that in like the Google SRE book would be called SLOs or SLIs, service level indicators, service level objectives. These are your latency guarantees you're trying to comply with, that sort of thing. And having detected some critical signal that doesn't look very good, the second activity is, as much as it saddens me to say this as the CEO of a vendor that helps with root cause analysis, it's not really realistic in a distributed system to expect anything to literally solve your problem for you. It is realistic if you have a sufficiently sophisticated system to refine your search space. The number of possible root causes in a microservice architecture is growing super linearly to the size of the architecture. So what I mean by that is if you go from 10 services to 100 services, you're more than 10xing the number of possible problems in your system. It's much worse than that because these services interact in mysterious ways that can't be easily predicted. So when you're dealing with an outage or even with a steady state latency problem that's been bugging you in P99 for months, in either case, your biggest problem is refining the search space of possible hypotheses. Once you have the right hypothesis, it's usually not terribly difficult to validate that hypothesis. And then once you've done that, the fix is often alarmingly easy, despite the weeks or months that can go into finding these things. But discovering that is a matter of refining a search space that's growing much faster than our own systems. Excuse me. And so I would argue that it's often the case that I see very intelligent people attempting to solve this search space refinement problem by visualizing the entire search space. So we see this usually takes the form again of giant dashboards, which is why I said to be wary of giant dashboards. I don't mean to say they should never exist, but you probably shouldn't expect them to be very useful during an emergency. And I would argue they're probably at best suboptimal in terms of doing steady state analysis of systems as well. So this is something that I don't hear this talked about as much, and I think it's pretty important. My last lesson is something that's near and dear to my heart. At Google, we're dealing with a problem in terms of cross-service visibility, and some folks came together and built a prototype of this thing called Dapper, which is their distributed tracing system, which I spent a long time working on and built that team out and eventually wrote a paper about it, which you can read if you're having insomnia someday and you need some help getting sleep. You can Google it and read it. But we had this issue that we solved with distributed tracing. I don't think that this webinar is long enough for me to go into a full speech about what that is, but I will try to give a really quick overview of what distributed tracing is for those who aren't familiar. So the idea here, I've drawn a diagram that's supposed to evoke microservices. You know, you have these things, some are bigger than others, they do different things. And ultimately, these architectures are responsible for transacting with end users in some capacity. And so you have a transaction that will enter the system and propagates through many services before it's done. And all that distributed tracing is taking these microservices and then literally tracing how a single transaction at a time propagates through these systems. And so it sounds pretty simple, and conceptually it's actually not difficult to describe. What you end up with at the end of the day is a timing diagram that spans service boundaries and allows you to understand at some level of detail what actually happened for a specific transaction at a time. So that's it. And it's really useful in that ordinary transactions in microservice architectures will involve tens or hundreds of different services. So if you're trying to understand what happened with a transaction and you don't have a distributed trace to lean on, it's nearly impossible to understand the macro effects that are taking place in these systems. So that's distributed tracing. Sounds useful. And we spent a while kind of struggling with this technology at Google and getting it to a point where it was actually really usable and useful and valuable for the entire company. And that's what the Dapper paper describes, I guess. I think it's important, though, if we're talking about tracing, to discuss its fatal flaw. It does have an Achilles heel. And I want to briefly discuss that before I'll get to my final point and my lesson learned from Google. So let's talk about the distributed trace, and let's talk about how much of this trace data actually exists in a distributed system. So this is kind of the multiplication challenge. At first, you have the transaction rate. So if this is basically, if you're a business, you're servicing requests from end users or APIs or whatever it is, there's some rate of transactions, and that's something that scales with your business. And generally you want it to be high because that means you're making more money or whatever. But that's something that hopefully is getting to be pretty large as you grow. You multiply that times all of your microservices because transactions touch many services. So now each transaction is generating transactions time microservices-ish, order of magnitude amount of data. And then you need to take all the actual telemetry data, which involves things like the timing, the trace IDs, a lot of tags, something that looks a lot like logging data. That all needs to get sent over the network and stored somewhere. And then you need to retain this because the traces are only useful if people or systems can take advantage of them. So you have to retain this data for some amount some period. And at the end of the day, you multiply this together, and it's just way, 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 way too much money, at least in a system like Google's. And there's no way around that. It's a law of nature, at least at the scale that Google is operating, that doing all of this was not going to happen if we were trying to centralize all of the data and write it to disk. So we made a compromise, which was to sample aggressively. So this is what we did with Dapper. So at some level, you have this theoretical idea of how much tracing data there really is in the world. And that's all of the instrumentation that's being executed all the time. And so by definition, I'm going to call that 100% of the data. And then what we did with Google is we'd flip a coin, and the second a transaction began, we would discard 99.9% of them just by fiat without even letting the thing start. And that optimization was an 1,000-fold improvement in the amount of data that we had to centralize because we'd thrown out 99.9% of it. Obviously with some caveats in that if there's anything interesting that happened in a transaction and you sampled it out, it's gone. And then there was actually a second sampling stage, a 10x sampling that took place between regional storage and global storage for Dapper. So when it was all said and done, we only retained 1 out of 10,000 requests. And the paper is very clear about the savings that we accrued by doing it this way. But going back to one of my earlier lessons about choosing the right scale, Google's systems are pretty unusual. I think their published number that gRPC has published is that Google's doing 2 billion RPCs per second globally. And that was the system that we were designing against. And this design decision was, our hand was forced, I think, by that data volume to a certain extent. I really don't think it was the right thing to do, even for Google, for many of the services. For a lot of services at Google that weren't web search and weren't ads, Dapper wasn't actually that useful because they had such a low request volume to begin with that by the time we'd thrown out all but 1 out of 10,000, there wasn't much left for them to actually examine. And certainly if you're looking for an outlier, it was probably gone. So this was a serious consideration for Dapper, but something we didn't have much of a choice about because we were forced to design for the largest systems in the world, which is not actually allowing for much of a feature set. What we've done with Lightstep, and this is the part of my presentation that I admit is a bit of a paid advertisement, but I think it's actually pretty interesting and relevant as well, is that we do sampling, don't get me wrong. As I said, it was a law of nature, and it is. Like if you operate at extreme scale, and most of our customers do, you do need to do some sampling somewhere, but we've moved that sampling to a very different place, and we're actually able to centralize that top number, the 100%, we can centralize into in-memory regional storage in what we call our satellites. And this has allowed us to build what's more like a stream processing system than a tracing system, where we can do all sorts of aggregate analysis, as well as, of course, trace assembly on demand via the global SaaS. This architecture has been a real eye-opener, I think, in terms of what's possible with a tracing system, at least for me, and is my biggest personal lesson learned from Google was, frankly, a lot of regret about the way we designed Dapper. I was 24 when I started working on that, and I had no idea what I was doing, and we kind of chose the easy path. Lightstep is something that I think is a lot more difficult to implement and require. Frankly, our staff is a lot larger than the Dapper team when we started at Google, but we have been able to build something that gives us some capabilities in terms of tracing, but more importantly, in terms of the search space reduction I referred to earlier in the observability piece that I would have salivated over at Google. So this is what we've tried to design, and it's meant for a scale that that befits large growth companies and significant brands, but is designed for a world outside of Google where we don't expect everything to be perfectly factored like we did with Dapper. So I'm almost done. This is what I want to review. So there are 2 drivers for microservices. Both are reasonable. Team independence should be the main one. If you're in the rare situation where you have a computer science problem that's so profound you need microservices, I salute you, and I think that sounds really fun. But most of the time it's team independence. So make sure that that's really the decisions that you're making are about team independence and not about just crazy scaling for scaling's sake. You should know how much you're scaling to and don't design past that. The services can be too small. This is my dig on serverless. I think serverless is important, and for what it's worth, Lightstep supports it and everything. But I've seen people move, I think, a bridge too far in that direction, and just be thoughtful about it. Look at the engineers, the numbers every engineer should know, and make sure you're actually designing the right size service. My hippies versus ants analogy, I'm curious for feedback about that. I have a draft blog post expatiating on it a little bit, but I think we should be careful about independence. It's important, but make sure that you still have central control over cross-cutting concerns in any kind of system that you're building. And observability is about detection and refinement. I think I got into that, but I think we see a tendency when we talk to the market for people to just build giant dashboards and attempt to get as much data on the screen as possible. The goal, I think, should actually be to minimize the amount of data you put on the screen and to get a fast refinement. And finally, that it is actually possible to trace everything if we build with a different architecture. And that's, of course, what we've tried to do at Lightstep. I've restricted myself from the urge of doing a product demo, but hopefully if people are curious, you can take a look yourself. And I think that's all I've got. So I've left over 15 minutes for questions. I hope that we had a great attendance today, so I hope we have a few, and I'll hand it over to the moderator.
All right, awesome. Thanks very much. Yes, there's plenty of time for questions. We've gotten some in so far. We'd love to get more. So if you have a question for Ben, just go ahead and use your GoToWebinar control panel and submit it, and we'll get to as many questions as we can. Okay, Ben, the first question, can you revisit when microservices are a good approach for your project?
Yeah, absolutely. It's definitely a great question. I mean, in general, I think microservices, the decision to pursue that probably needs to be made at the level of an entire organization. And there's I was talking with one of our customers the other day, and this particular person who's a director of platform engineering, he was talking about how they initially called it microservices decomposition, and then they've kind of rebranded the effort of replatforming. I think decomposition made people think about compost and stuff like that, and wanted people to think more about replatforming. And what was necessary for them to get this thing to actually go well was to help everyone understand both why it was better for the company, but also why it was going to be better for them as individuals. So I think the concern I have about individual teams making the decision to adopt microservices is that they do it in isolation and there isn't buy-in from adjacent teams and from the rest of the organization. It can end up falling into that kind of hippies versus ants mode where everyone kind of makes the decision separately, and you don't have the kind of central controls that lead to a good outcome. So I think it's a wonderful thing to do as long as the team in question understands what they're doing and is being intentional about using some standard technologies that other groups within your organization are also using, so that you can amortize the cost of maintaining those particular design choices across the entire organization, probably with some kind of central platform team, rather than having every single team taking on the work of managing and deploying and operating a totally custom bespoke stack. So that's my only kind of word of advice. Otherwise, I think they're fantastic.
All right, great. Next question here. It sounds like Google started with microservices very early on, but for those of us who are starting with a mature software monolith, how should we structure an incremental migration to a microservices architecture?
It's an awesome question. Yes, there are many ways to do it. What I've seen, what seems to be most effective, again, reflecting conversation I had with an engineering leader and our customer base, I think they referred to their monolith when they started off this transition as a giant ball of mud. I think that was the specific language that was used, and the goal is to unravel that. It reminds me a little bit of unraveling like a really nasty knot, which I find to be enormously gratifying emotionally for some reason. But you have to find the threads on the outside and pull them off first. And so what people typically do is you start with your monolith, and then you build a very small ring of microservices around that monolith that are the easy things to take off. And so your architecture for a little while looks a bit like a pinwheel, where you have the monolith, it's still there and still pretty big, and you're starting to take some mass out of it and move it into a hub and spoke model. And then as things mature, the monolith tends to become a glorified routing layer. So that's usually the last thing to go. And most of our customers still have a monolith, if not all of them. And it's usually doing that work of just routing things from one service to another. But the services start to get more numerous. And before you know it, you've started factoring out certain common functions like authentication and things like that. And you start to have a proper mesh or web of services rather than just having this hub and spoke. But I think the best thing to do is to start small and aim to get from a monolith to having a monolith plus 8 services. Make sure that you choose those to be some easy wins, get the technology choices right, and having learned those lessons, you can go and split things out further. I have seen people try to just obliterate the monolith and do a full replatforming in one fell swoop, and that doesn't go very well.
All right, great. So let's see, lots of time left for questions. So please keep sending them on, and we've gotten some great ones in. The next question, any thoughts or guidelines on using microservices as external facing APIs?
That's a good question. I guess I can't ask for clarification on this medium, so I'll try to interpret that correctly. I apologize if I didn't, and you can resubmit. But microservices as external facing APIs. I think if I understand the question correctly, we're wondering whether the boundaries we use for microservices are well aligned with the boundaries we choose for external facing APIs. I would say they might be, but I wouldn't use that as a design constraint, or I wouldn't use that to motivate designs. Um, uh, the concern I have about going that path is that the service boundaries typically align with teams as much as anything else, and as an API becomes more popular, I imagine the load increasing and the service splitting in pieces, and then suddenly it doesn't align one for one anymore with the external facing API. That said, I think good APIs are good APIs, whether they're external facing or not. I think AWS famously has succeeded by designing its internal APIs in exactly the same way as it designs its external APIs, and that's been marvelously successful for them in terms of their own internal independence. So I think thinking about that as a motivating end goal for microservice API design might make a lot of sense, but I wouldn't use it as a litmus test.
Okay, I got a note saying that your interpretation was spot on. So yay. All right, great. So next question, thinking of the reporting use cases, when would you use microservices to expose data versus creating a data mart?
That's a really good question as well. I live in a world that's mostly online systems, so latency sensitive online systems, which is often different than that kind of world where you're dealing with a lot of data and you're trying to crunch it with some kind of reporting job or Hadoop job. I think the requirements are there are some similarities, but by and large, I don't think that microservices, or at least totally bespoke microservices, are as appropriate in the high throughput, high latency data processing pipelines as they are in the latency sensitive serving pipelines, mainly because you often are better off if you have to write custom code plugging into some kind of existing framework. I mean, obvious examples would be things like Spark and stuff like that. That said, I mean, they certainly have their place, but I would go back to my what I said earlier about trying to think about engineering management structures and teams as much as anything else. If it makes sense that you're going to have some component that's going to have a bunch of custom logic and it's going to sit there and be part of a system for that sort of data analytical reporting use case, then sure, I think it makes sense to put that in a microservice just like anything else. But it's a different world, that world, and the systems also look a lot different as a result. So I would probably need a little more detail to give a more confident answer.
All right, great. Next question. Are there any standard tools to help decompose the monolith?
Yes, I think the most hyped tool at the du jour would be the service mesh. That one, unlike a lot of things that get hyped, I actually really like. I think service mesh is fantastic, but it gives you a single piece of software that can be deployed separate from your actual application as a sidecar model. And I was saying earlier, I could find the slide, but there's a slide where I talked about how Google factored things out like RPC and load balancing and service discovery and all that stuff. Service Mesh does exactly the same thing for you in a sidecar process that you don't need to link into your actual application. And as a result, it can be used as a bridge between monolithic software and microservices that the monolith depends on and communicates with. So I think that service mesh is a wonderful way to get a lot of bang for your buck. It also is not, it's not a skeleton key that just unlocks distributed tracing, but I do think that distributed tracing is table stakes if you want to make sense of these systems, and service mesh gives you a nice hook to get a lot of valuable tracing data, and for that reason I think is an important piece of technology to consider if you're looking for additional leverage in that migration.
All right, great. Next question. Are there any rules of thumb to decide how many microservices are required to migrate from a monolithic app?
Yeah, I mean, I guess I would say that there can be too many. I talked with, I will not use the name, but I was talking with a very enthusiastic team of 5 people who were at a big enterprise company. So this isn't some kind of Bay Area startup. It was a giant enterprise everyone's heard of. And this team of 5 people were maintaining 400 services. I think that's admirable in the sense that it's kind of amazing they got that many services per person, but they were totally drowning. So I would maybe go back to what I was saying earlier about organizational charts and to think about assuming the engineering team is built out along functional boundaries in terms of the monolith. It might be a good rule of thumb to look at how many teams and how many components are actually in that monolith. And expect something similar in terms of the number of distinct services, which is different than the service instances, right? If they scale horizontally, you could end up with 100 copies of a single service, but I'm talking about the service type. You'd probably have roughly 1 service type for each distinct engineering team that's maintaining some component of a monolith. Again, that's just rough, but if you're asking for rule of thumb, that's what I would give.
Okay, great. We're about 8 minutes to the top of the hour. We do have time for maybe 1 or 2 or 3 more questions. So keep sending them on in and we'll keep spitting them out. Next question, is there a debate about, there is a debate about each microservice should have standalone database versus microservices can share one database. What do you think?
Oh, that's a good one. Of course, the answer is it depends, but I'll try not to dodge it quite that easily. How does it depend? I think that the determinant for me would be whether the database is being shared for operational convenience, as in, we don't want to deal with 2 MySQL instances, so we're just going to create one. And then these different services that have completely different needs and are in different schemas and so forth can, just kind of run amok in the same instance. Or if they actually, I guess if we're talking about relational databases here, but it could go for any kind of database. If there's a need to join the data between the different services at the database layer, if that's anticipated, barring of course constraints around scale and stuff like that, I would argue that it makes sense to share the databases. Doing joins across different databases is a total nightmare and is something that should be avoided at all costs unless you have no choice. If it's about operational convenience, it really comes down to what sort of database activity we're talking about. It seems like there's, roughly three categories. There's the easy category where it's not very intense and you just occasionally write and read from a database and nobody cares. That stuff, in my mind, just put that in some shared instance and forget about it. If it becomes a problem, it'll be easy to fix. There's the case where the workload's more intense, but it does fit in a relational database. Like you're not going to run out of space, but the load is significant. In that case, I would try to separate things for operational reasons, because you don't want to have shared fate for a database. It's just so catastrophic when it will fall over, unless you have some kind of really sophisticated multi-tenant provisioning system, which almost nobody has. And then the third case is data that's so large that it has to go in some kind of NoSQL database, or something that's itself a giant scalable system. And then I think you're really in a different category. You have to consider how sophisticated your own internal team is for managing that, or of course if you're using a managed service and Azure or AWS or Google, how much faith you have in their ability to separate things from a quota standpoint. But in those systems, it really isn't. It depends. I think it depends a lot on the team you have that's maintaining that shared resource and so on and so forth. But by and large, I would argue to separate the scaled out use cases unless they actually need to join with each other, in which case I don't think you have much of a choice but to put them in the same place.
Okay, great. We have time probably for one more question here. At what point in new product development would you start to use a microservice architecture?
Oh, that's a really good question. Well, I mean, I had the situation. So we started Lightstep 3.5 years ago, and my co-founders and I are all pretty technical and know this microservice stuff pretty well. And I will say with confidence that we avoided it at first. I think while we were prototyping and trying to achieve product market fit, we did it in a few specific places. I mean, going back to our architecture, we have this thing called the satellite. We built that thing really early because the company literally depends on that. I don't mean from a product standpoint, but the company isn't going to make sense unless the architecture works. So we built that almost immediately, but mainly to validate the hypothesis that it was possible. With the exception of the satellites, we were attempting to get to product market fit with as few microservices as possible. Because if you're doing quick changes and you have to cut across dozens of services, it really does slow you down. At this point, now that we are much more scaled out and have many more engineers and customers and so on, we have what I would refer to as a real microservice architecture. But I think for any product team, we should be using microservices only if you have to test the hypothesis about scale, which is going to be vital to the success of your product, or if you have no choice from an engineering velocity standpoint, which at some point everyone does. But we don't subscribe to the idea that you should do microservices from day one, like it's the only solution. I think for product market fit, pre-product market fit, it's hard to beat a single piece of software you deploy very easily and quickly with a small team.
All right. All right. Great. Well, that is all the time that we have for questions. So I do want to thank everybody who did submit a question. If you submitted a question and we didn't get to it, I apologize. We do have all the questions here, and the folks at Lightstep will be receiving a copy of all the questions. So I'm sure somebody will be more than happy to follow up with you on post-event. I do want to remind the audience that today's event has been recorded. So if you missed any or all of it, or if you just want to listen to it again, you will have the opportunity to do so. We'll be sending out an email with a link to the webinar on demand after this event, and it will also include a copy of the slides for those of you who asked about them. The webinar will also live on the devops.com website, so please feel free to take a look at it there. Just go into the webinars tab under on demand, and it should be right there waiting for you. While you're there, take a look at some of the other webinars that we have both upcoming and on demand. Hopefully there'll be one or two that pique your interest. Ben Siegelman, thank you so much for giving such a great presentation today. There were a lot of questions, so I know the audience got a lot out of it, so thanks very much.
Really my pleasure, and I put my email up there because I like getting email from people, so don't be shy if you want to talk about any of this. I'm happy to chat about it. I think it's fun.
Awesome. Awesome. Great. Well, again, thank you all for joining us today. This is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody.